So, hello everyone, welcome to one more webinar from the Wells Technical Committee of the SP Brazil. I'm Nicholas. I'm the part of the board of the SP Brazil Technical Committee's office in the area of the marketing and communication. And now on, we will have Fuad with us, talk about learning and flow test interpretation, a stability analysis approach for ensuring web integrity. As you can see, this webinar will be all in English because Fuad is not Brazilian. So to all of you understand, this webinar will be conducted in English. So I would like to invite everyone who watching us to follow our technical page of the Wells Committee Office in the LinkedIn. In this page, we will publish a series of webinars, mini courses, and technical forums that will be in the next months. With me, we had Danilo. Danilo is the co-chair of the Wells Technical Office, and he will share with us about the next events planned to the committee. So before all, I would like to invite you all to ask questions to Fuad. All the questions in Portuguese or English will be answered in the end of the presentation. And follow our LinkedIn page, follow SPA Brazil too, and become SPA member because a few benefits of the committee, technical committees, will be all available for SPA members. So become a member from SPA. It's easy. It's sometimes no paid if you are a student. So become a member. It's the better to do. So I will call Danilo, the co-chair of the Wells Technical Office, to talk about the next events and about the committee itself. Welcome, Danilo.
Hi, Nicholas. Thank you. I'm going to switch a little bit to Portuguese just to present about the committee, the Wells Committee, and then we can go back to English. Então, pessoal, boa tarde a todos. É um enorme prazer estar aqui com o Nicholas e com o nosso colega Fuad, moderando esse webinar. Eu agradeço aí a participação de todos os que estão conectados agora conosco e também aqueles que vão assistir depois. E antes de começar, né, o webinar, eu queria falar um pouquinho aí sobre o nosso comitê de poços, né? O comitê de poços, ele está atualmente estruturado dessa forma. Ele é um espaço interessante aí para promover o debate, a troca de experiência entre os profissionais e também promove, né, a realização de vários eventos como esse webinar que a gente está acompanhando aqui hoje. Então, ele está organizado aí em 6 grupos técnicos: o de perfuração, completação, abandono, intervenção, e aí o de integridade e o de resposta à emergência. Lembrando aí que o de integridade é justamente quem está organizando esse webinar de hoje com o Fuad. Aqui tem um desenho, aqui um organograma da nossa estrutura. A nossa chair, né, é a Maíra. Eu estou aqui como co-chair do Comitê de Poços. E aqui a gente tem aquela estrutura com os 6 grupos técnicos, né? E cada grupo tem um chair. Aqui o chair nosso aqui de integridade, a Maíra também é chair, eu também estou aqui como co-chair. E eu aproveito, inclusive, essa oportunidade, né, para lembrar que a gente está, no momento, sem chair e co-chair aqui no GT de abandono. Então, se alguém souber ou tiver interesse, né, de se candidatar, só mandar aqui um e-mail para esse endereço aqui, ctpoços.spe@gmail.com. Então, só mandar aqui um e-mail, seja para se auto-indicar ou indicar alguém, lembrando aí que o chair, ele deve ser um membro filiado à SPE. E aí eu reforço a fala do Nicholas aí, para que vocês se filiem à SPE, não só para a participação aqui no Comitê Técnico de Poços, mas uma série de outros eventos, além de acesso a publicações técnicas que vocês terão como membros do SPE. Então, essa aqui é a nossa estrutura, e eu deixo também aqui um agradecimento mais do que especial para todo o time de apoio, desde o time de comunicação até o time que organiza, planeja esses eventos, né? Então, aqui estão as carinhas dessas pessoas aí que correm atrás para que esses eventos sejam possíveis. E aí, ao longo de 2025, a gente tem planejado 3 tipos aí, basicamente, de eventos: os webinars, esses encontros online, como o de hoje, eles ocorrem, inclusive, com emissão de certificado, e aí metade desses eventos vão ser abertos ao público, como o de hoje, e metade desses eventos vão ser exclusivos aí para membros da SPE. Mais uma razão aí para a gente se filiar à SPE. Os fóruns técnicos, eles vão ocorrer exclusivamente, né, para os membros da SPE, e eles podem ser tanto presenciais quanto online. E aí vai ter um tema específico para ser discutido nesse fórum, e os minicursos também exclusivos aí para membros da CPE, gratuitos e com emissão também de certificado. Então, fiquem aí ligados na nossa agenda, porque a gente vai ter outros eventos ao longo de 2025. Aqui, para quem quiser, né, se filiar aí, se filiar não, para quem quiser fazer parte dos comitês técnicos, aqui tem um QR Code que vai abrir um formulário para vocês se cadastrarem nos comitês técnicos, né? Então, fiquem à vontade aí para usar a câmera e pegar esse QR Code, ou também compartilhar aí com os colegas. Então, aqui vocês podem se juntar ao SPE também, tem um QR Code aqui para isso. No cadastro, tem um e-mail lá que pede um e-mail de referência, e aí fiquem à vontade tanto para usar o da Maíra quanto o meu e-mail. E se vocês aí quiserem se filiar ao comitê, como eu já mencionei, também tem um formulário específico para se filiar ao nosso comitê de poços. E fica aí também o convite para vocês acompanharem a página do nosso comitê técnico no LinkedIn e também a página de todos os comitês técnicos também no LinkedIn. Então, tem 2 QR Codes aí para vocês acessarem. Então, esses eram os recadinhos que eu queria dar aqui, pessoal, antes da gente partir para o nosso evento. E aí, now I will switch to English again and welcome our guest for today's lectures, Fuad Rahimov. So Fuad holds a bachelor's degree in petroleum engineer from Azerbaijan State Oil Academy in his hometown Baku, and a master's degree in petroleum and natural gas engineering from Middle East Technical University in Ankara, Turkey. Over the past 12 years, he has held various roles in the oil and gas industry, including reservoir engineer, field engineer, well integrity engineer, and well integrity engineer team lead. Fuad currently works as a senior well service engineer at Kuwait Energy Basra Limited, where he is responsible for completions, well interventions, and well integrity. His core area of expertise is well integrity engineering management. Fuad, the floor is yours. You have about 1 hour to give your presentation, but we don't expect a hard stop. Thank you very much.
Hello. Thank you, everyone. Thank you all for having supporting for me. I'm gonna use the slides that I presented in Abu Dhabi. As a start my presentation slide, but as a first note, even though I'm gonna go through all the slides, but I expect everyone, like if anyone has questions, you can just ask questions. You don't have to wait until the end, or you can wait until the end. I mean, both options are fine with me. Okay, I'll start the topic now. This is about the line and flow test interpretation, use of eigenvalue stability analysis. This is based on my latest SP paper that presented in Abu Dhabi on 4th of June 2025. So before delving into the line and inflow test interpretation, just brief overview of what inflow test is. I mean, we all know what inflow test is, but just as a reminder, we do the inflow test to test unhold barriers in the direction of flow. Sometimes we test liners or sometimes bridge plugs whenever the well is handed over from completion stage to production stage, and our normal the final test prior to well handover process. So The linear inflow test is performed while reducing the hydrostatic head for an underbalanced state and where flow is induced. And if the barrier is tight, then we should not see any continuous flow, and the test is accepted. So the question is how much pressure differential you apply during the linear flow test. So based on we'll take the standards across the industry like NOR 10 or ISO 16530-1 or 2. We say that this industry standards say that the linear flow tests should be tested to the maximum expected pressure the liner will be exposed to while life cycle. Okay. Well, actually, in my experience, the lightest place we can go is water. It's not practical to inflow test the inflow test the liner with using lighter food and water. I've never seen using nitrogen for the linear flow test. This is just not practical, and that's why I added one more clause to the requirements that whenever it's feasible, inflow test the maximum expected pressure differential. But the best industry practice is just to use the fresh water. Okay. Why this topic? Why we should be concerned about how linear flow test is interpreted? Basically, as of now, or as of recording this presentation, there is no one-to-one standard across the industry. Whether it's NOR 10, whether it's UK oil and gas, whether it's ISO 16530, either dash or 1 or 2. There is no one-to-one standard dictating how inflow tests should be interpreted. I just took some, I just present some 3 standards. Actually, 2 of them are standards and one is a technical book that use may term or can term, but there's no shall term. There is no hard requirement on how to interpret this test. So let's first look at the first standard, UK oil and gas well life cycle integrity guidelines. It says Horner plots may be used to differentiate between pressure buildup due to a leak and thermal effects. API RP 96, 2013. Horner plot may be necessary to evaluate the results of the inflow test, which would require monitoring shut-in pressure at the choke manifold versus time. And there's one more book, Crampton's book, Well Control for Completions and Derivations book. Actually, both of those standards that I mentioned before, UK oil and gas and API RP, even though these standards loosely refer to Horner plot for interpretation of linear flow test, but there is no standard framework how to apply Horner plot for example thermal diffusion problems. How would you frame your linear inflow test acceptance based on the Horner equations to decide if the barrier is holding or not? There is no framework. It just says may be used. But the only one book, this is Crampton's book, Well Control for Completions and Interventions book, that provides some guidance how to apply Horner's plot. Says create Horner plot of flow rate against Horner time on the x-axis and draw a straight line between sample points. If the line intersects x-axis before infinite time, which means Horner time equals to 1, the leak is diminishing and inflow test is good. And if the line crosses x-axis first, then the test has failed. We'll come back to this graph later on, but the main important point is to mention that there's only one technical book that I could find, and there are some also well-controlled manuals that also refer to this methodology on how to apply in Horner plot for this problem. But as of now, there is no hard requirement. So this is the Crampton's book. Okay, so for this successful test, the book requires the line intersects the axis before infinite time. The leak is diminishing and the flow test is good. Okay, so if the plot makes an intersection of the x-axis, it means that there's flow at infinite time and the inflow test has failed. Basically, if you look at the plot on the right side. Okay. So on the x-axis, you have Horner time. On the y-axis, you have flow rate. So it says if the Horner plot, if the straight line crosses x-axis first, so that means when that line crosses x-axis first, so that your y-axis is 0. So that means test is accepted. But if the red line crosses y-axis first, which says the flow rate has some finite value, so that means the test is not successful. That test is failed, and then you will interpret the test as the failed test. So just based on this intersection x-axis or y-axis, the test is interpreted as pass or fail. And just as a side note to this note, why it's so important. When the well is handed over from completions, from drilling site to completions, in the handover stage, there is an inflow test. Okay, and usually the well is handed over to completions when you have 100% sure that your liner is inflow tested and it's good to go, because you are going to set the pattern across the 7-inch liner. Okay. And if the test is ambiguous, if you don't have clear result of the liner inflow test, then you have to extend the test, and which costs additional rig time. And the rig time, I don't want to go the value, but it's a considerable amount of money. So because of this constant pressure of rig time, constant pressure of resources to interpret the test, people just roughly use this method to expedite the process and then go over the completion stage, regardless how linear inflow test looks like. So, however, Horner technique is not applicable for thermal diffusion problems. I summed up four main criteria why Horner technique cannot be applied to thermal diffusion problems. So Horner technique, for some of you who have reservoir engineering background, or just as a generic note, Horner technique is derived for the PTA, pressure transient analysis, well test purposes. So it says that during the PTA pressure test analysis equations, there is line source solution. Probably the best book for this line source solution is a Dake's book. This is the classical reservoir engineering book. And for deriving the Horner technique for its original purposes, which is the pressure transient analysis, it says that infinite reservoir size relative to the wellbore radius, which means that regardless of the pressure perturbation, you will not see any pressure drop across the edge of the reservoir, even though you have some pressure waves propagating across the reservoir, your wellbore has not seen the pressure perturbations. That's why it says infinite reservoir relative to the wellbore radius. That's the original core premise of Horner technique for the original pressure transient analysis. However, during the liner inflow test, we are getting flow during the first 2 hours or 3 hours sometimes because of the heat, because of the thermal flow expansion, and because of all the thermal expansion happening around the wellbore radius. So that doesn't make wellbore radius non-negligible. It's not negligible because you have thermal expansion right in the wellbore radius, right across the radius. So that makes this assumption pretty much invalid. Data linearization. So if we come to the next, I will show on the next slide. The original pressure transient equation is inherently linear equation. And for the thermal expansion problem is actually nonlinear, which has the exponential decay function. Now there are, I mentioned in the paper, now there are some techniques that you can make to your nonlinear equation to make it linear. Okay, and there's always some methods to linearize the nonlinear function, but you will lose all the inherent assumptions of the original nonlinear nature. When you linearize nonlinear nature, you lose inherent assumptions for the nonlinearity. That's what happens with the thermal expansion for the line inflow test. When you linearize original exponential decay function, you lose all the wellbore conditions that are not valid anymore. We'll come to the next slide to be more clear. So inherent assumptions also for the original Horner, as already mentioned, derived for the pressure transient equations, which assumes there is single phase, constant temperature, and constant fluid properties. However, during the landing flow test, temperature is constantly changing. And because of the change in temperature, you are getting flow. And because of this single factor alone makes Horner technique invalid. And there's also in the PTA analysis, pressure transit analysis, and it says that there's only single phase oil, most oil. However, in the landing flow test, you have wellbore, original in-situ wellbore, which is typically mud, and then you have the tested fluid, which is water. Okay, so you already have two phases of fluid anyways, and both two phases, both the fluid properties will constantly change as a function of temperature. They are not constant, and that's why it's not applicable to the inflow test. Inconsistent function asymptote. Okay, that's a little bit key parameter as well. So in pressure diffusion analysis, right in the next slide, it's described. So in pressure diffusion analysis, the function asymptote, which means that whenever your key variation reaches to infinity, what's gonna the function will look like? Okay, if you're the function asymptote in the pressure diffusion analysis is the initial reservoir pressure, which serves the core premise of all the pressure transit analysis anyways. In thermal diffusion equation, it's not the same. It's the initial product volume. I will go to the next slide to make it more clear. Okay, so in the above equation, we use the volumetric expression after superposition. So to give it basic, the first equation is the volumetric fluid expansion. Okay, in the second equation, this is the original equation for the pressure transit analysis. This equation serves the original purpose of Horner. This is the second equation, and the first equation is the fluid volume expansion after applying superposition principle. So because of the similarities of these two equations, people decided to use, the Horner technique. However, in the second equation, as the delta T reaches to infinity, the function asymptote is Pi, which is the initial reservoir pressure, which makes sense because in the pressure transit analysis, we are after the initial reservoir pressure. That's what we are after anyways. In the first equation, however, your function asymptote is Vi, which is the initial fluid volume. However, you don't do inflow test to see your initial fluid volume. We are not after initial fluid volume. We are after the final fluid volume. If the final fluid is going to decay to zero, or it's gonna be some constant value throughout the test. In other words, your Horner equation for the pressure diffusion, your key parameter that we are after is Pi, reservoir pressure, which is exactly not the same in the laminar flow test, because laminar flow test, we're not after the initial fluid volume, we are after the final fluid volume. That's why you have this key inconsistency across both equations, invalidating the applicability of this Horner equation. Okay, so coming back to the stability concept in the context of heat transfer. So what's stability concept anyways? So whenever we say the equation has reached stability, we assume that the function reached to zero. Okay, why stability? Because it's not dependent on time anyways. Regardless how much you change your t parameter, regardless which variations you change, your final function value is zero. That's why we say the function reached its stability. And applying to the heat conduction problem in the second equation, it's a little bit complicated because heat conduction problem is part of the differential equation. However, stability concept applies to ordinary differential equation. So basically, in the heat conduction problem, we have two major variations that the function is changing. That's a function is the key equation is a function of. wellbore radius, and T time. Okay, so we have radial variation and we have temporal variation. That makes the equation complicated because you have a partial differential equation. So basically, we have to solve this equation, or rather, we have to decompose this equation to ordinary differential equations so that we can apply stability concept to solve the equation. I don't want to go to the all the complexities how this equation is solved. It's in the paper, but it suffices to say whenever we say stability concept, we mean function reaches to zero, and that function has to be ordinary differential equation. However, heat transfer equation is partial differential equation, and we have to decompose in ordinary differential equations. In this slide, we have to show the stability concept in action. This is I illustrate on this equation as you see. So you have this red line, and anything above the red line, you see the function converges nicely downwards, converges to the red line, and anything below it converges upwards, reaching to that red line. In that red line itself, the function is zero. Anything above it will go nice to converge to zero. Anything below it will converge upwards, reaching to zero. So whenever we say the function is stable, we mean this v in the sample equation is 49, because exactly in that value your function will reach to zero. For some reason, the equations are not showing here properly. But I will just describe those equations without going to variables. Okay, so basically in the first equation we have the partial differential equation, second order, which is the underlying equation of the heat transfer equation. Okay, however, there are some assumptions to this equation. So we have to, as mentioned already, in order to be able to apply stability to this equation, we have to decompose this to ordinary differential equation, which is dependent on single variable. Because this equation is dependent on R and T, now we can take R and T functions and then solve this equation. Again, for some reason, we don't see the equations itself, but for the purpose of this presentation, it suffices to say that the fluid volume expression is actually the thermal expansion, which is the e to the function lambda t. I don't know why, again, it cannot be shown here, but this is the exponential decay function, the final fluid volume expression. If you solve this heat transfer equation, you will end up with the exponential decay function, which is a key premise of this concept. Homogeneous and non-homogeneous boundary conditions. Okay, as we mentioned, the heat transfer equations has to be decomposed to ordinary differential equation. But there are two key assumptions: homogeneous and non-homogeneous. What homogeneous and non-homogeneous means? Homogeneous means that at the edge of the wellbore, you have the temperature is zero. Okay. Non-homogeneous means that you have internal heat generation, which means that at the edge of the wellbore, there is some finite temperature value. So why do we care about homogeneous and non-homogeneous boundary conditions anyways? Because during liner inflow test, when you flow test a liner, you have the cement hardening process, because you just cemented the liner and then you run a hole with your surface string and you set the packer and you decrease the hydrostatic. But meanwhile, the cement hardening still continuing on. You still have the exothermic process, which emits heat, which have internal heat generation. With internal heat generation, the temperature across the wellbore is not zero. You have some finite temperature value anyways, and that's why the equation, the partial differential equation that mentioned before, the original heat transfer equation, has to be solved with the non-homogeneous boundary conditions. And with the non-homogeneous boundary conditions, you still end up with the exponential decay function. When we say exponential decay function, we mean e to the power minus lambda t. Okay, e to the power minus lambda t. So based on this exponential decay function, which we discussed, for the linear flow test acceptance criteria, there are we derive two acceptance criteria. Number one, as we mentioned, e to the power minus lambda t, because your t is positive, it's time, it's saturation, it cannot be negative, it's positive. Okay, for the full volume to be zero, that lambda, which is the eigenvalues, has to be positive. Why positive? Because you have the exponent term is negative, which is minus lambda t. Because t is positive anyways, your lambda has to be positive so that the exponent term remains negative. So e to the minus lambda 2 will decay to zero if the lambda is positive. Otherwise, if lambda is negative, minus, the exponential will just go up, which will just blow up from the origin. That's why it will not reach stability. Whenever we say stability, as mentioned, we mean a function to reach to zero. And for the function to reach to zero, your lambda has to be positive, because positive with negative exponent term will drive function to zero. And if you remember this, the direction field in the previous slide, all the arrows, little arrows, pointing towards the red line, it will appear minus the converge to the red line. Acceptance criteria number 2. On the acceptance criteria number 2, I don't want to go to the math details, but if you look at the plot on the right side, you have just a couple of peaks. You have, I just mentioned 3 peaks. In the actual test, when you do the linear flow test, the amplitudes of these peaks of this function should consistently decrease. The reason why they should decrease, because e to the minus lambda t, because you have lambda squared. Whenever lambda is higher, because it's negative exponent term, it will go down. If your lambda is positive and if lambda is higher, it will decay much faster because the exponent is negative. However, if the lambda is negative, as mentioned already, it will just blow out from the origin. This is nice visualization. Again, this direction field is the ordinary differential equations term. And whenever we use this direction fields, it's much easier to visualize the inflow test. So in the left side, you see this zero line, and you see all these little arrows pointing towards this zero stable line. So whenever the e to the minus lambda t, okay, this is I will just keep repeating throughout the whole presentation, e to the power of minus lambda t. Whenever this lambda is positive, because exponent term is negative, that will drive the function to reach to zero. That's exactly what you see on the left side. However, on the right side, if your lambda is positive, because if your lambda is negative, because the minus lambda t, if lambda is negative, then negative product will be positive, and it will just blow out from the origin. That's why you see all the red lines pointing away from the stable line, because of this positive exponent term. I will answer all the questions. I know there was lots of questions. So that's a very nice theory, okay? That's a very nice theory, but what about its field application? I will just make a note that in my current workplace, we had pretty much nearly 3-4 years of data, and I applied it to the last 2 years of every single inflow test that we performed in our workplace. Even though I did not include all the single tests, but I chose the most prominent ones, the most obvious plots that are easier to explain, because sometimes you have some measurement noise, sometimes you have the data that's a little bit inaccurate, and that will just introduce some noise and some randomness to the test data. So that's why I picked particularly those results that are easier to visualize and with less inaccuracies. So there is 5 process that we have to go through if we want to apply this to the inflow test. So as we mentioned, exponential decay model. So whenever I just took the line inflow test data, even you go to the Excel and you go to all the test points and you go to try to plot a chart, and the very first thing you will notice that the chart has very nice curve. Even though you don't know all these equations, even though you don't know all the partial differential equations, solutions, you just draw this raw data from the field and go to on the Excel and go to the insert equation on the chart. It will give you exponential decay function. That's the science in action. Whenever I remember just vividly, whenever I saw this, I was fascinated because that's science in action. That's theory in action. Because the raw data gave me exponential decay function. And when you go try to solve all those equations, regardless boundary conditions, homogeneous, not homogeneous, you still end up with exponential decay function every single time. And whenever you draw the raw data from the field data, you end up with exponential decay function from the Excel. And however, for this analysis, I used the nonlinear Python data matching, and Python also gave me the exponential decay function, which accurately describes the nonlinearity. So based on this exponential decay function, you go to the compare the lambda if it's positive or negative. If it's positive, as already mentioned, because of the positive, because your t is always positive, so your exponent term will always stay negative, and that will drive your function to 0. So we have to just verify that the function actually follows exponential decay function. Okay, that's the first thing we check. That's the very first thing. And then you check the eigenvalues. You check whenever we say eigenvalues, we mention we mean the lambda, e to the power of lambda t. But why eigenvalues? Well, we have to see the equation, but eigenvalues is a central topic in linear algebra. Okay, is an ideal parameter, and because we are lucky that the equation is exponential decay function, which introduces lambda as an eigenvalue, that will give you much easier answer to understand how the function will behave if you extend the test. Because if you extend the test, if your lambda, which is your eigenvalue, if it says positive or says negative, and the key question why we call eigenvalues, because it will drive you both temporal variation and it will drive you both spatial variation, which means you have to be able to answer the question of how temperature changes in both time domain and in both space domain. And because lambda appears in both equations, in both time and space domain equations, then you have to be able to have at least 2 acceptance criteria, one for each. Acceptance criteria number 1 captures this temporal variation. Acceptance criteria number 2 captures spatial variation. And then you have to segment the data into 4 or 5 points. Usually, the best practice of these inflow tests is to extend the test at least 360 minutes or 240 minutes regarding your test duration. But my personal experience, I've never seen the data that's valid and that's robust anything less than 240 minutes. Any data less than 240 minutes, you still have some random noises. You still have some inaccuracies. You still have some ambiguities in the data. So you have to extend the test beyond 240 minutes. In some rare cases, I saw 180 minutes test in some rare cases, but the best practice 240 minutes. And then you have to segment the test into 4 points, into 4 sections. Each, let's say, 60 minutes, or if it's 180 minutes, or if it's 360 minutes, then you have to extend segmented test each 90 minutes, and then track down the amplitudes of the temperature variation. So that's exactly what we followed. In the plot, this is from the raw field data, okay, on the right side. So in the x-axis, as you see, I'm not using corner time. I'm using the just minus time on the x-axis. On the y-axis, you have volume, which is in liters, okay? So this is exactly what I mentioned just a couple of minutes ago. Even if you don't know the your final solution of transient heat equation, you see that this is the exponential decay function. I mean, if you just click on the equation, it will give you exponential decay function. And because of this lambda, as you see in the red box, it's positive, which means that e to the power minus lambda t, and when your lambda is positive, and t is always positive because it's 10 duration, and then it will nicely drive your equation to 0. So when you apply this nonlinear matching with Python, so you have original fluid volume, which is 9.62 liters. Okay, this is fitted data. Actual data on the field was 9.2 liters. Okay, and then you have to based on this the accuracy of the match, we introduce the residual stress error and coefficient of determination R squared. So R squared is 0.98 and the RC is 0.32. Actually, for the nonlinear, I prefer RSC, residual stress error, which is actually is a little bit more representative data rather than R squared. The reason why, because residual stress error gives me an absolute volume. It's kind of in the same units of the parameter that you are after. It's not squared. It's not it's not root squared like r squared and then root square of r squared. It is kind of the absolute unit volume that you are after. That's why it gives me a typical picture on how accurate my data is. Typically, if your RSC is based on my practice, if it's less than 0.4, in some cases, if your RSC is less than 0.45, you are in a good shape. You're in a good shape in terms of match. Anything above it, extend the test. So, as mentioned just a while ago, there are 2 stages, right? Early stage and late stage. So the test, as you mentioned, as you see here, is lasted here 300 minutes, but here it lasted the first stage 160 minutes and then 250 minutes. So in the first stage, you see the exponential decay function. You still have exponential decay function anyways. I mean, there's no doubt about it, but you still have some data that's falling a little bit apart from the best curve. However, in the late stage, as you introduce more data, you have a more accurate match. And if you look at the mean squared error, and if in that case your R squared is pretty much the same, your mean squared error in the second stage is actually less than in the first stage, which again, triggers that you have a better match relative to the early stage. So computed eigenvalues evaluation. So in that case, we are following, remember we said the original fluid volume during the landing inflow test follows exponential decay function, e to the power minus lambda t. That's exactly what we are talking about. So now we will say computed eigenvalues evaluation, we are tracking down those lambdas on the equation and see how lambdas are changing throughout the test. So the first stage, let's say within 15 minutes, your decay rates are initially very, very high, and due to rapid initial decay, because as mentioned, the exponential decay function, you have e to the power minus lambda n squared t. If your lambda is very, very high, because it's negative square negative square term, that will drive the equation much faster, because it's in the exponent negative and it's squared. That will drive the equation much faster, and that's exactly what we see in the first 50 minutes. You have decay rates are very high. In the mid stage, let's say the 50, 150 minutes, eigenvalues, which are lambdas, tend to stabilize, and you have some occasional spikes persisting throughout the test, probably because you have non-homogeneous boundary conditions being more obvious, being more pronounced, and that's why you have some spikes. And the late stage decay rates, if you see the decay rates here, it's around 0.0175. Okay. In the late stage, decay rates reduce significantly. If you see here, you reach even below 0.0025, which is the late stage. I mean, in that stage, your lambdas are very low. Okay, I mean, that's why you see this slower rate of decay of lower eigenvalues. This is another test. I believe this is a little bit easier to explain. In that chart, you see the continuous decay of lambdas, continuous decay of eigenvalues, and the decays are still very high in the first 50 minutes, amounting to 0.025, and then which is even below 0.005. So the reason why, because again, the solution to I have to go back to the solution of the thermal diffusion equation, because that's a key equation of this problem, because the equation itself introduces Bessel's equation of the zeroth order first kind, and whenever you have this roots on the x-axis, and whenever you have high lambdas and it's in the negative square term, if it's higher, because it's negative square, it will drive the equation much faster. That's exactly what we'll see. If lambda n gets lower, let's say 1, 2, and you have slower rate of decay because it's negative square term. Okay, this is a very interesting chart. This is my favorite part. Horner technique is with different t values. There's a little bit ambiguity in selecting the logarithmic expression, because in the logarithmic expression of the original Horner technique, okay, which is the logarithmic t plus delta t divided by delta t, okay, and then t plus t over delta t plus 1, okay. So t0, that's a very problematic variation. That's a very difficult parameter. So your t0 should be exactly the same parameter whenever you have some temperature variation, some temperature change across your wellbore. Your t0 should match that exact time frame. And that's very hard. You don't know. You have cement hydration, you have fluid circulation, you have, and then during the laminar flow test itself, you have thermal heat effusion, which also change the temperature. Which T0 values you should take? So that's why I took two T0 values, 60 minutes and 240 minutes. And then you see, if you look at the 60 minutes, the chart is a little bit problematic. It's ambiguous. It doesn't cross x-axis as per standards of Crompton, or not standards, but rather than let's say framework, or how do you word it, by Crompton. It doesn't look like it's gonna cross x-axis, but doesn't look like it's gonna cross y-axis either. So we have to extend the test to see which way the test is progressing towards. In the other chart, you have T0 240 minutes. And in that case, we have to extend the test. And if you take T0 as 240 minutes, arbitrary number, 240 minutes, you see the plot crossing y-axis. If it crosses y-axis, so that means you have some finite flow rate, which means that your test is failed. But in the first case, whenever your T0 is 60 minutes, you have to extend the test and see if it passes or if it fails the test. So it's a little bit ambiguous. It's very, very hard to know which T0 value you should take. We should take 60 to 140, 180 minutes. I mean, it's very ambiguous. That factor alone, for me, that randomness of this T0 alone gives me an indication that Horner cannot be applied to this problem, because there are too many variations that you cannot possibly describe and explain. And whenever you take that the same test data and like split into 4 segments, which is let's in that case you have 300 minutes of test, right? And if you split across each 4 segments, okay, that's the equation that I was talking about nonstop. AN is your coefficient exponential to the minus lambda alpha lambda t. Okay, this is your coefficient. This is the lambda is your eigenvalues. Okay, and this y J0 is your Bessel's equation, 0th order first kind. So basically, to put it in simpler terms, this Bessel's equation drives your hot temperature changes across the space domain. This exponential function captures temperature variation across the across the temporal domain, and this AN is your just the coefficient based on the boundary conditions. Basically, this will dictate how high your curves are in the Bessel's chart. Okay, so when you take these 4 segments and not linearly feed using the Python, it will give you these 4 variations. If this C, which is your amplitude, okay? So basically this coefficient, this product of AN with exponential decay function is your C, okay? And this product drives the amplitude of your Bessel's equation, which is Y0 lambda n R. And across the 4 segments, you have this C progressively going down, and your lambdas, which is your eigenvalues, progressively going down as well. And the reason why, because if your lambda is very, very high, because it's squared and negative in high lambda n, it will decay much faster. That's negative squared term. But if it's lower number, it's 1 or 2, it will decay much slower because your lambda n is slow. That's exactly what's happening in this chart. To put in simple terms, because as the time progresses, your lambda, your high numbers, your high eigenvalues, drive the equation cause the function to decay much faster. And when the test progresses, then you have this slower decay of function because of your lower lambda n. This is exactly what you see here. And this, if you, okay, let me go back to this equation. So just if you look at this equation, okay, as mentioned already, this part is your amplitude, okay. And when you the multiplication of this amplitude with exponential decay function is your amplitude. And when you again track this amplitude across 4 segments, you will see continuous decay of this C amplitude numbers, which is again, I know one of the questions will be why here you have minus lambda n squared, but why you have here minus lambda. The reason is because this minus lambda n squared is your computed value. This minus lambda is your fitted value. Because this directly, whenever you have lambda, this directly comes from the field data. Comes directly from the data you have. But whenever you have minus lambda squared, this is by textbook. This is the solution of the original transient heat equation. But whenever you have this lambda positive, and T is always positive anyways, this should go down to 0. And this amplitude should progressively decrease because of the changing values of this lambda n. I believe that was the end of this slides. I know there are lots of questions. I'm all ears. Any questions? But I don't know why, for some reason, those equations are not properly shown here. Those equations are not properly shown here, which makes it very, very hard to explain this concept. But I assume you guys have the access to the one Petro that we can download the paper, and maybe we can then go over the paper to explain it much more clearly, because without this without these questions on system, it's very, very hard to understand. But at least we have this equation here. Luckily, I could find it, that explains the phenomena. Whenever this lambda is positive, this t is positive, it will drive the equation to zero, which is your acceptance criteria number one, and this is your acceptance criteria number two. Back to you, Nicholas, if anyone has any questions.
Okay, Fuad, thank you for your presentation now. I'll call the leader to stage to restart the discussion, but before all, I had a question. I remember studying test so I remember the storage effect and the skin effect have a such significance. Oh, okay. I remember storage effect and the skin effect had a such significant presence in this kind of test. So can you explain the effect of storage in the wellbore as the skin effect too?
Wellbore storage?
The let me remember the effects of the storage in this type of test, the inflow test. I remember in the graduation type that storage has a such huge effect in this type of test.
Okay, so just to understand the question, so the effect of inflow test, you mean, right?
Yeah.
Okay, basically the reason why like it triggers so much attention, because usually your packer is set across 7-inch liner, okay, and your liner lap is above the production packer. And the reason why it's so important, because if your liner lap fails a test, your leaks during the well life cycle, you will have all the wellbore effluents in your A annuals. And that will give you sustained casing pressure in your A annuals. Usually your 958 is P110 casing. And it's not resistant to wellbore effluents if you have high H2S. And corrosion is the main bounded mechanism to cause a well integrity issues. And there are lots of failure mechanisms that we can go through if you have hydrocarbons in annuals, but it suffices to say that you have hydrocarbons in the 958 that's not designed to contain that wellbore effluents in your annuals.
Yeah, thank you very much, Fuad, for the presentation. I have two questions actually. Although the inflow tests are not my expertise, I have seen some tools that aim to reduce the test duration by extrapolating the pressure behavior over time and concluding whether the test will pass or not. I'd like to know what are our thoughts on that, and if the equations you presented can you run in real time, or do you have to wait until you can analyze the results and then infer if the result of the inflow test? Can you comment?
Okay, sure. Let me take the first question. So the first question you mentioned that the data extrapolation. Well, usually that's exactly what people are doing right now, the extrapolating data, because what the industry is saying is that take the original Mandelian equation, extrapolate, linearize, and try to figure out the next value. However, when you linearize the data, you lose all the original assumptions, because the heat transfer. Let me say this first. During the line flow test, the very reason that you are getting flow is because of thermal expansion. The dominant mechanism is the thermal expansion, which is original not linear. It is not linear function. It's exponential decay function. And whenever you try to linearize exponential decay function, you end up with logarithmic expression. And that's why people ended up using Horner, because you have logarithmic in Horner equation that's used for pressure transient analysis. So because of the similarities, people started using Horner equation, but not for the original purpose, which is the original usage of the well test. Now they are trying to use logarithmic expression for the inflow test, but for original the exponential decay function for nonlinear equation. You can do it mathematically speaking. You can linearize every single nonlinear equation. You can every single nonlinear equation itself is linear if you zoom in one single time step, and you will see this linear trend anyways. But if you zoom out and take the big picture, the heat transfer itself is not linear. But when you make a judgment, when you try to, okay, my liner passes the test or doesn't pass the test, you do not zero in on the last 5 minutes or 10 minutes test data. You look across the all test data for 360 minutes or 480 minutes. You look across the whole test data. Which original, when you zoom out, then you have to honor the original nonlinear equation. If you are, let's say, assessing the test based on the last 5 minutes, I would argue that I will agree that you can assume that's linear, because every nonlinear equation within this limited time frame is linear anyways. But when you assess a test based on 360 minutes, then you have to honor the nonlinear nature of the original problem. And that's why it's not applicable. The second question, you mentioned that can we track the on life? Actually, we can, but the best practice is just to monitor returns from the trip tank. Let's say in every 10 minutes, 15 minutes, and you get the value from the field, and then you compare your lambdas, your eigenvalues, and then you see. Is it positive? Is it negative? How your amplitude change? You can do it like after getting the data. Usually, it like in either 10 or 15 minutes, depending on how the component structure. But usually, it's in either 10 minutes, you are getting this flow or fluid volume or flow rate from the field in every 10-15 minutes. So you can calibrate your model in every 10-15 minutes until you get the R square, let's say 1, or your RSA 0.3 or less than 0.4. I have never seen any reliable data less than 240 minutes. And the reason why, because it's the process is so slow, the thermal expansion, the heat diffusion, it's so slow process. You have to wait enough data you have to be able to understand the exponential decay function. Remember, if you don't have exponential decay function, so that means your data is not validated yet. It's not reliable. You have to see the pronounced exponential decay function. If you don't see it, then you have to wait it.
Yeah, perfect. Thank you. I ask this because, well integrity is key for us. So the result of the test is very important, but also we have a drive to try to reduce the time, the duration of this kind of test, especially in offshore environments where the time is really a lot of money. So that's why I'm asking that, to try to balance those two values.
Just if I may say so, my my current is in Iraq, is onshore, but my previous role, I was in Caspian Sea, offshore, and you have 6,800 meters HPHT gas condensate wells, and you have to test your land and flow test. What we were doing I remember vividly. Okay, I have the drilling engineers running at me. I was at the time volunteer team lead, and they were running at me. Okay, why weren't accepting the test? I have rig time. I don't blame those guys. I mean, every single one of us, it was in our KPI also to reduce rig time as much as possible. But you don't want to compensate. You don't want to compromise your well integrity because of additional cost. Because if you rush and accept the test, and down the line, if you have the leak in your liner, you end up spending even more.
Yeah.
You have to. You cannot. I was through it so much times with my colleagues. You cannot save the world if you have hydrocarbon in the annuals. You have no justification. You cannot save the world. If your 958 leaks, if your production casing leaks, 1338 is weaker than 958. Basically, the world is gone. And I do understand. I'm in both teams. I'm in drilling team. I'm in well integrity team, but I'm from well integrity. But what I want to try to message that it's not just my job as a well integrity. It's well integrity is a part of job. Every single technical person in the company is just not up to well integrity engineer job. It has to be every single person's key focus working in oil and gas industry.
Yeah, true.
Yeah.
So I think we don't have more questions for this webinar. So I think that's the end. So Danilo, would you like to talk about the next events of the committee, to your final considerations too?
Okay, Nicholas, thank you. I just want to thank again Fuad for this important subject that he brought to our technical committee. This last discussion, I think it's very important. We cannot compromise safety and integrity. And sometimes by trying to do so, we can have even a worse scenario, even more cost in the future. So we have to think every time about long-term integrity. So it was a really nice presentation, very complex. I want you to read the paper to see equations, but it was very interesting. You make yourself very clear on the explanation. So just thank you.
Thank you. Thanks everyone for having me. I hope it was helpful.
Okay, thank you, Fuad. Thank you, Danilo. Hope to see you all in the next opportunity. And I think that's the end of the webinar. Don't forget to follow us in the social media and to keep and watch our webinars, our mini Qs, and our next events. So that's all for today. Thank you all. See you next time.
Okay, thank you.
Thank you. Bye-bye.
Thank you.
Bye-bye.